Okay, in this video we're going to talk about how to tell when a solution to a differential equation exists and how to tell when that's the only solution, so when it's a unique solution. Now you might say, well, who cares? I mean, if I can just find the solution, then I know if it exists and I'll just be done. I don't need to worry about, why do I need to know ahead of time? Well, the answer to that is it's not hard to write down differential equations that are extraordinarily difficult to solve. And so we would want to know whether the solution exists before we dive in and try to find the solution. And moreover, it's not hard for me to write down a differential equation right now that you don't know how to solve, that we haven't talked about how to solve yet. And so let me do this. Let me give you an example. What are we looking at here? Here we go. Okay, so for instance, we've been talking about differential equations of this form, okay? Where am I on the screen here? These are the types of differential equations that we're looking at in this class, okay? Let me just give you this one. All right, is this something that we know how to solve? Well, we've only talked about two types of differential equations. We've only talked about solving two types. The types we know how to solve, well, the first type we talked about was, and we kind of eased into this type, but then we settled down and we realized that, oh, you know, all the things that we were solving up to that point were just of this form. All right, linear differential equations that look like this. So we know how to solve that kind. Excuse me. And we know how to solve this kind, the kind that we can put into this form. And this is what we talked about in the last video, a separable differential equation. So linear differential equations and separable differential equations. We can, if they can be put into this form, we know how to solve them. All right. Is this of either of those types? Well, it's not linear because it's got a square on the y, so it's not one of these. Right? Is it separable? Can I write it like this? Well, I can get the y's on the left. I can subtract the y squared. All right, so I can get all the y's on the left. But can I write it as a function times of y times y prime? No. Subtracting y squared is not going to do it, right? It's not going to be a function of y times y prime. So it's not going to be one of these. So this is a differential equation, very simple one, that isn't of either types that we know how to solve. So I would like to know, though, does a solution exist? Let's suppose we go a little bit further here and we specify initial conditions. I say I want to find the solution of this with initial conditions y of 0 equals 1. Does a solution to this exist? Well, let's take a look at one thing we do know how to do. We talked about this in a previous video, is look at slope fields. Okay, let's go ahead and take a look at the slope field for this and just get an idea of whether it looks like a solution exists. Okay, so I'm going to write that in here. Our differential equation was y prime equals x squared plus y squared. Okay, so this is the slope field. And I want to find the differential. Our initial conditions were that y of, what were they? Y of 0 equals 1. Okay, so y of 0 equals 1. So does it look like there's a curve that goes through this point that follows this slope field? Well, it sure does. And in fact, this program will draw it out for us. Oops, I'm not on the right screen. Okay, so y of 0 equals 1. Yeah, there it is. There is the curve, right? So clearly it exists just by looking at the picture here. And in fact, I could specify different initial conditions. I could start at different points. And it looks like pretty much wherever I start, I have a solution. Look at this. Pretty much any initial condition that I start with, maybe anything, it has a solution. So this differential equation clearly seems to have solutions by looking at this picture. Now, pictures can be deceiving, right? I mean, there may be subtleties to here that we're not seeing. I mean, the picture is just a sketch. We're seeing it from afar. So what we would like to have is a mathematical, rigorous way of talking about whether a solution exists. And that brings us to the first theorem that we're going to discuss. Not the first one that's appeared in your book, but the first one that we're going to talk about. I've been saving the discussion for theorems till now because I don't want to. I'd like you to be focusing on the meat of what we're doing and not jumping ahead and using the results of theorems before you understand what's going on. But this theorem we are going to talk about. All right, and this is theorem 2.3.1. So that means just to emphasize the way the notation works. The first two digits here are always the section that the theorem is in. So this, we know this is in section 2.3. That's the section that we're in right now. And then this number is just the number of the result in the section. So the first result happens to be a theorem that the book is discussing, so they label it 2.3.1. If you go scroll down in the book, you'll see 2.3.2. Might be a theorem, might be an exercise, might be an example, something else. But that's how the notation works. The first two numbers are the section that we're in, okay, the chapter and the section. But what does this theorem say? It says that if f is continuous on an open rectangle. Now, what is the f that they're talking about? Well, they are talking about differential equations of this form. Let me tone down my contrast here. All right, we're talking about differential equations of this form. All right, so the f is just the right-hand side of the differential equation, y prime equals f. So they're saying that the function f is continuous on an open rectangle. So we have some rectangle here. So you're saying, see, why is this a rectangle? Because we're saying that x is between two numbers a and b, and y is between two numbers c and d, and that makes a rectangle that contains x0, y0. Then the initial value problem has at least one solution on some open subinterval that contains x0. Okay, let me put that into perspective by going back to the picture here. I'm going to put some transparency here. Okay, so what was our differential equation? It was y of 0 equals 1, right? So that means it's going through the point 0, 1. Our solution is going to go through the point 0, 1. Right? So our initial condition specifies the point that we go through, and that's the point that we specified right here. And so the theorem is saying make a rectangle around that point. Okay, so there it is. So if we have a rectangle around this point, and the theorem said if the function is continuous in this rectangle. So what was our function? Our function is x squared plus y squared. Is that continuous in that rectangle? Well, these are continuous functions of x and y, and so yes, it's continuous everywhere. So in particular, it's continuous in this rectangle. So if it is, then a solution exists. And there it is. You can see the curve. I mean, this program has sketched the solution for us. And so this theorem is telling us that yes, a solution does exist, provided we can verify that the function is continuous in some rectangle. Now, you may need to make the rectangle somewhat small, right? For this particular example, the function's continuous everywhere. So you can make this rectangle as big as you want, right? Because the function's continuous everywhere. But if the function had some discontinuities, you might need to make this rectangle small enough so as to avoid those discontinuities, because we need the function to be continuous in this rectangle. So we might need to shrink this rectangle down to a very small size so that we can guarantee that the function's continuous. Okay, but if you can find such a rectangle, this theorem is guaranteeing that a solution exists. Okay, so let's see what else the theorem says. In part B, it says if both f and fy, that means the y derivative of f, we're going to differentiate it with respect to the y variable, if those are continuous in the rectangle, then 2.3.1, that's this, the differential equation with the initial value condition, has a unique solution on some open subinterval that contains x0. Wait, isn't that what we just said? Well, no. This says at least one solution. This says unique solution. Key word, unique. Unique means it's the only one of a kind, right? So this part B is telling us that if you can further verify that fy is continuous, then we know that there's only one solution in that rectangle. Now, in the example that we were looking at, where we had x squared plus y squared, yeah, the derivative, what's the y derivative of this? If you take the y derivative of this function here, differentiate this well with respect to y, you get 2y. That's linear, that's continuous, certainly is. So we know that the solution is also going to be unique. And that's why this program is able to draw one and only one curve through that point. So the theorem's guaranteeing that that's the case before we even look at the slope field. Okay, let me take you down to look at some more. We have y prime equals sine of x times y. Is that, well, let me draw the slope field here. Is this continuous with respect to x and y? Yeah, sine is a continuous function. Multiplying it by y, that'll still be continuous. This is continuous everywhere. The derivative is just, with respect to y, is just sine x. That's continuous everywhere. So again, we have a unique solution through every point that we choose. Right? Any point that we choose gives us a unique solution. I don't need to know how to solve this to know that a solution exists. The theorem is telling us that. Let's go to another one. Y prime equals y over x. Okay, it might look good so far, right? If I move this point around, there's one solution that goes through every point, right? But let's look at this function. Let's look a little more closely here. This is our function, f, right? Now, let's let's just ask, is it continuous? Well, here we have to be careful, right? When the denominator gets close to 0, we start running into trouble, right? In fact, this function isn't even defined when the denominator x is 0. Not even defined, so it can't be continuous. Okay, so the theorem is telling us that a solution is not guaranteed when x is 0. Now, what do they mean by solution? They mean a function of y. See, a function of x. Y is a function of x, right? So they're saying that there's no function of x that's guaranteed to exist. Now, it might exist, but it's not guaranteed by the theorem that would solve this differential equation. Now, can we see that by looking at the slope field? Well, if I move this point so that the x is near 0, or at 0, what happens to this line? It goes vertical. Is that a function of x? No, a function of x can't be a vertical line, right? It's not passing the vertical line test, so that doesn't work. And so, yeah, there's a curve that works that goes through the slope field, yes, but is it a function of x? No. And the theorem's telling us that. It's saying that if we choose any initial condition so that our point is on the y-axis, no solution is guaranteed to exist. And in fact, no function of x does exist. Okay? Let's look at the next one. So in this one, it's pretty much the same, right? The function here is discontinuous when x is 0. So I'm not getting solutions when I position my point on the y-axis, right? No solution appears here. And moreover, when I get close to x equals 0, what's happening? Look, it's a mess. Look, the program is having a hard time guessing what the solution might be. And we have to keep in mind that that's what the program is just guessing. The program is just sampling points, actually in a little rectangle. It's sampling points and saying, I think the solution probably goes through here. It's doing guesswork, all right? And we can see that it's having a hard time. We can see that things are getting really mucked up over here. Now, like I said, the program's sampling points in a rectangle. So why is it getting mucked up? It's choosing a rectangle that's too large. Okay? Remember, our rectangle has to be small enough so that we don't contain a discontinuity. Now, if I position this point, if I position this point close to the x-axis, sorry, the y-axis, I need my rectangle small enough so as not to include the y-axis, because the y-axis is where we have the problem. That's where x is 0. Okay, so my rectangle, this rectangle is much too big. It's including the point x, the y-axis where x is 0. So if I zoom in here, zoom. If I took a rectangle this small, I don't hit the y-axis, and now I'm fine. Now I'm fine. A solution does exist through this point, and the theorem guarantees it. As long as my rectangle doesn't hit where the discontinuity is, the function's continuous in here, I get a solution. But as soon as that rectangle gets so large so as to intersect the y-axis, well, function's not continuous, theorem doesn't guarantee a solution exists in there, and we can see all kinds of stuff goes wrong. Okay? Let's look at our next example, y prime equals tangent x. Okay, this one's actually fine on the y-axis, but it's got some other problem points. Where does tan x cease to be continuous? When x is any multiple of pi over 2. So when x is a multiple of pi over 2, we can expect to have problems. Well, the theorem is telling us it's not guaranteed that a solution exists. And you can see that's exactly what's going on. When I get over here to pi over 2, it's a mess, right? And in fact, at pi over 2, there is no solution that exists. The computer program's trying to make something, but you can see something's going wrong. Okay. And then my favorite here is this one, y prime equals square root of y. Actually, let me replace this with 2 root y. It'll make it easier when we work with this later. And look what's happening here. I'm only getting solutions above the x-axis. Now I can get a solution no matter where I put this point, right, up here, but no solutions exist down here. Why is that? Well, because this function doesn't even exist when y is negative. Okay. Now, is this function continuous? This function's continuous everywhere it's defined. All right, but remember the other part of the theorem. The other part of the theorem asked us to check, for part B, it asked us to check the y derivative of f. Okay, let's take the y derivative of this. If I take the d by dy, what do I get? I get 1 over the square root of y. Is this continuous? It's continuous until we get to y equals 0. And then we have that problem of dividing by 0. So this is not continuous when y is 0. Not continuous at y equals 0. So look what's going on over here. As we move the point near the x-axis, what's going on with the solutions? Well, it looks like there actually is a solution down here. Now, does that make sense? Well, according to the theorem, a solution should exist provided this function's continuous. And we said this function is continuous at y equals 0. It's up to y equals 0, so a solution does exist. And what we're seeing is that it just is a horizontal line. And so yeah, a solution does exist. Now the question is it unique? Well, for this we look at the other part of the theorem. The other part of the theorem says that if the derivative with respect to y of the function is continuous, then we know the solution is unique. But we just said that, oops, the derivative with respect to y is not continuous. So maybe this won't be unique. Okay? Theorem isn't saying it definitely isn't. It's just saying it's not guaranteed to be. Right? So what's going on here? Well, I see I'm getting a horizontal line. Is that the only solution through this point 2, 0? Well, look, if I lift this off, and I just move this over here, right there, look, I got another one. I got a curve that's coming down and hits the point 2, 0, and then I know that the horizontal line is a solution, so it looks like I'm getting another solution. I'm getting a solution that comes, the computer's not drawing it, because the computer's too dumb, right? But we know that the horizontal line is a solution, right? So we know that there's a solution that is horizontal up until we get to here, and then lifts off, and then comes up this way. And we're seeing this right part of it. That's one solution. And another solution is the one that's just horizontal all the way across. There's actually two solutions here. So yes, a solution does exist, and the theorem guarantees it. But the theorem's telling us that the solution's not unique. There may be more than one. And that's what we're seeing here. We're seeing more than one solution. We're seeing this one that just goes straight through. And we're seeing this one that lifts off once it gets to the point number 2. Now, was that the only time we saw this? In fact, we saw this happening before. I just didn't highlight it. When we looked at this differential equation, y over x, we were actually seeing this before, because when I get a curve for pretty much, as long as x is not 0, I'm getting curves that go through pretty much any point. But what if I choose the point 0, 0? Is there only one curve that goes through this point? No, in fact, all of these curves are going through that point. So if I start with the initial condition 0, 0, I have an infinite number of solutions. There's not a unique one. There's not just one. All of these are going through the point 0, 0. Definitely not unique. Here's actually an infinite number in this case. And so the theorem's saying that that could happen. And that's exactly what we're seeing in these two examples. Okay, so in this video we took it just kind of an overarching view of this thing, kind of just looking at the picture and talking about it from pictures. In the next video we're going to do things a little bit more analytically and look at these functions actually solving them out and looking at the theorem and seeing what it can tell us. So I'll see you in that video. All right, so see you then.